Okay, so today's gonna be super easy. We're just gonna go through some Python stuff. I think I've already said this, but it turns out the stuff that we want to do in Python is really easy to do in Python. So when I prepared this lecture, it only took like 5 minutes to do all the things. So we're going to go through some basic stuff. Your Capstone project, so the main part of the course here for you guys is bringing in that .wave file, doing the analysis to try to decode the message. So that's what we're going to talk about today. We're talking about how to import a .wave file, how to play a .wave file, and then how to get it into an array and actually look at it so you can do stuff with it. And stuff like that. We're also going to talk about how to like synthesize some signals and stuff. And that's actually going to be your project. You're going to make a little synthesizer and upload a song. So let's get into it. Yes, we are recording. Oh, nope. Upload my picture. Okay, so the first thing we're going to do is we're going to want to do some plotting. So actually, take that back. The first thing we want to do is import a .wave file. There's a library. There's a number of libraries to do this. The one I really like, and the one you're going to use a lot, is called SciPy. If you're not sure how to do it, you do the how to install. You do the pip install SciPy. No, because it helps you spell it correctly. SciPy, like Python. Yeah, it's already got it. But so you pip install SciPy. It's scipy.io. Import, and the library is just called Wavefile. And if we want to import that, we can import it with a function that is just wavefile.read. And I'm going to grab that Cantina band 3.wave. It returns two things. The first thing is the sample rate, and the second thing is the actual data, right? The actual signal itself. It just comes in a straight up Python list. So, what's up?
So, I know that like how do you
How do you check and or change the directory that the WAV file's in? You just move it to a different directory. I'm not sure.
I guess
Maybe I don't understand the question.
How do you check like what directory?
If you import the system library, you can do a directory movement.
So Edward, was that you? Or is it somebody else?
Yeah, if you import the system library, you can do like directory, like CD, stuff like that.
Yeah, this one, the sys library.
Yes.
Well, yeah. So this one lets you do a bunch of like file system stuff. The easiest thing is just put the WAV file in your same folder with your Python file. Yeah. I mean, you can do other stuff. Like if I was to say, if I had like data and I had it in, and I moved it in there, right? I'd have to specify the directory I was in. But it lets you start the root directory, which maybe is what you're getting at. You don't have to do. I know in other languages you have to do this business of like putting together the path, starting at C or whatever. Python is Python, so obviously it doesn't care. It just says I'm here. So whatever you start with, that's where you're at. If you want to go backwards, you do the .. to go back a layer in the file system. That kind of was that how you're doing? Okay. Yeah. So like in most things, Python makes it easy. You don't have to do any like file path building or anything like that. Because Python is good to us. All right. But if you did want to do that, this library, the sys library, the system library, handles basically everything you could possibly do with the file system or your operating system. There's also is it OS? Yeah, there's an OS library which handles jacking with the operating system. So, all right. So we imported that. Let's take a look. Let's just kind of read some stuff. Print the sample rate is. Remember, if you're doing like string concatenation, like with a number, you have to cast it as the string. sample rate per second. Let's give that a shot. No. The heck did that happen? From. Oh my god. What have I done? What's up?
Spacing got me lost a lot, but I didn't realize the spacing I used to have a space out and it's just.
You use space. First off, let's talk about the fact that you use space instead of tabs.
Yeah.
What do you like? Why are you like just a psychopath? You really think I want to go 4 spaces? I feel like about it. He broke up with his girlfriend because she used spaces instead of tabs. Yeah, don't do that. But yeah, Python is tab delimited, so it does everything is based off the tabs. I mean, yeah. Congratulations, you're officially an old guy now. You're like, nah, I want my brackets. I want this new tab elimination. Okay. Oh, it's because I was showing stuff with the file system, and now it's all angry at me. Oh, it helps if you spell the. But you have to spell the file name correctly. Cantina Band 3. There we go. So yeah, so we can print out the sample rate. Sample rate is 22,050 samples per second. Let's see. Print. There are samples. There are 66,150 samples. So how long will the file be? Then the audio should last. So how do we figure out how long the audio is like this? Batman. So the number of samples, the length of the data divided by the sample rate. Seconds. Boom. So the audio should last 3 seconds, which makes sense because it's. But if we go back to the thing, yeah, you guys can't see it, but it is 3 seconds. That's why it's named Cantina Band 3. So yeah, so that's the basic deal there. I mean, we could do, if I wanted to print out the data itself, obviously I'm not going to be able to see the whole thing. But, you know, everything is in a list there. It is a list. For the type. Oh, now it comes out as a NumPy array, which is like a list. But it's a little easier to work with. So it's working, it's doing NumPy. NumPy is another library that you're going to use, which does a bunch of. It speeds up the math. Basically, the fact that it makes up for the fact that Python doesn't have arrays in the traditional sense. It just has lists. So it adds array functionality. So if you want to do, it also adds a bunch of cool stuff like convolution and doing FFTs and stuff like that. Now you're allowed to use those sorts of things. Yeah, so that just comes out in an array basically, but you can also treat it like a normal array. You index it the same way, you can splice it, you can sub-index it and stuff like that. Cool. So the last thing I do is look at it. And for that we use matplotlib, .pyplot, as PLT. PLT.plot. I'm not going to do anything fancy, just plot the data. PLT.show. And hopefully it'll let you see this. No, you can't see it. Bounce over here real quick. Show me the figure. Okay. So now you see, it is indeed a waveform. Yeah, there we go. That's a better way to do it. All right. So there we go. So that's kind of the basic thing there, right? If you can do that, you can pretty much do anything else, right? You can read in the waveform, you can get it as an array, you can visualize it. All is good, right? From there, it's just a matter of figuring out what the heck is going on in that array. So next up, let's do this. I'm not sure. No, I don't do that. Let's move on. Did I forget a thing? No. Okay. There's one more thing. Give me just a second. It was in my notes, but it didn't make it into here. Python. Sorry, I tried to screenshot everything I was doing, but I seem to have forgotten. Okay. So the next thing I'm going to do is let's go ahead and play the audio. So maybe you want to listen to it. So I'm going to say play a .wave file. The library we're going to use for that is called Simple Audio. Yeah, it is, isn't it? Yeah, your figure. I'm going to store it into ECE. I think I probably need to import it here on my laptop. I was doing a lot of this on my desktop at home yesterday. Okay. So the first thing I need to do is create a wave object. So the way Simple Audio works is ECE.wave object from the wave file. This isn't quite how I did it yesterday. And 3.wave. So that's just how we read it in. And then we need to play it. And to do that, we're going to create a play object. .play. And what we want to do is we want it to sort of synchronously hang up until it's done. I'm going to comment out the guys there. Guys in Discord, were you able to hear the music by chance?
No.
Yeah, okay. We're not going to fight with that. But if you could have, you would have heard it playing. The guys here in the classroom heard it. I'll play it again for me. So you see the sort of terminal there hangs up. It waits. It synchronously waits until it's done playing music. I wonder, actually, can I print? No, I'm just curious. Music is playing. Will it keep playing while I'm just on? So you can do other stuff. So you can keep running while the music's playing, or you can just stop and wait. So yeah, so that's how we can play the .wave file. All right, the last thing we want to do today is I want to create and play a custom waveform. I'm going to comment out. Nah, leave it. Who cares? I like it. And this is what you guys are going to have to do for your project this week. I haven't posted it yet, but this is going to be it. All right, we need to define some parameters ahead of time. So like frequency, Let's go with 440. That's 440 hertz. It's a C in music. Let's go with a sample rate of 44.1 kilohertz. These are some just sort of standard values. And let's also, how long do we want to play for? Let's go ahead and play for 3 seconds. All right. So the first thing we need to do is define our, essentially our horizontal axis, right? That in, we need the sort of in values to bounce off of. So I'm going to go ahead and shorten NumPy to MP. And NumPy's got some useful stuff for us for that. So I'm going to say in is equal to mp.linspace. If you ever use the linspace function in MATLAB, it's basically the same thing. We start at 0. We're going to go until seconds. And we're going to go in the steps of seconds times the sample rate that we just defined. And that'll give us our sort of horizontal axis to build our signal on top of. All I'm going to do here is build my signal. Signal equals MP. MP has a bunch of math functions like pi and also sine and cosine and stuff like that. So we're going to use sine. Now we're going to define our signal. 2 times pi, so MP.pi, times n, so 2 pi n, times the frequency. That's going to give us our signal there. One thing we want to do is we want to normalize the signal since we're going to play it. If we weren't going to play it, we don't really care about this. But we want to make sure that all the values sort of fit inside of a box. So if we say, well, we're going to make it a 16-bit signal, we're going to do signal norm equals signal times 2 to the 15 minus 1 divided by the maximum value of the absolute value of this signal. So all that says is whatever signal times the largest value that 15 bits can hold or 16 bits can hold divided by the largest value that appears in the signal. What this does is just normalizes it and shrinks it down. Have you ever blown out a speaker or even turned up the volume too long, go too far, and you start getting weird noise? You start getting distorted? Yeah, in fact, this is what if you use a distortion pedal, that's what it does. Right, it blows the signal past the range of what can be put out, so stuff starts clipping. So to prevent our signal from clipping, we decide, all right, we're going to make everything just 2 bytes, and we're going to normalize our signal to that, so everything sits in there and we won't get any clipping. Yeah, it is an async function, which is nice. Okay. Let's see. So the last thing I'm going to do is I'm going to cast it to a 16-bit signal. So I'm going to say audio equals signal._norm.as type mp.int 16. A lot of when you're watching this class, if you take DSP with Dr. Nutter or something like that, everything is going to be 16 bits. The board that he uses for that class is all the signals are 2 bytes long. So 16 bits is a pretty common word size for audio processing applications. So that's what we're going to do here. Now let's go ahead and play our thing. And I apologize for the guys in the Discord, you're just not going to get to hear it. Equals sa.play buffer. We're going to do the exact same thing we did with the wave file. We're just going to grab it from so instead of grabbing it from a file like we did before, right, from wave file, here we're grabbing it we're putting it in a play buffer. That'll just push out the stuff. Audio, number of channels 1, bytes per sample. So we did it at 16 bits, so that's 2 bytes per sample. So if we wanted to do more, we could have, but we didn't. And then we need to tell it what our sample rate is. So this packages it up nice and neatly and plays it. So we're going to go play object dot wait until done. I don't think I have a Python syntax highlighting thing on my laptop running. Okay, so I'm going to run this. We're going to hear the Cantina song again, and then we're going to hear the tone, although you guys won't hear it unless hopefully you're coding along, in which case you can play it for yourself and hear it. So that's a 440 hertz tone lasting for 3 seconds. You do that. No, that would have been cool. Okay, so that's how we created. I don't know. I think that's pretty cool, right? So we created a signal by putting a sine wave of a particular frequency in an array. We pushed it to a buffer and we played it out as audio. So the last thing we want to do is let's take a look at the Fourier transform of it. So you can see that signal content. We should see this, since it's just one sine wave, it should be a pretty clean Fourier transform. I'm going to do this mp.arange. This is also kind of setting up our horizontal axis for our FFT. So SP equals, oh goodness, where was it? Yeah, numpy. So mp.fft. The FFT library is weird. It's like a module inside another function, or function inside another module of the same name. So you can do, in practice, you should do a better job of importing this to make it a little more readable. But we want to take the FFT, the signal. We also want to do this frequency thing. All this does is sort of, you know how we've got everything. So the FFT function will just like give us the raw output of just like slapping our signal with the FFT. If we want to like put it nice and neatly on that, negative pi to pi kind of map, we got to do this frequency step, which basically just says, hey, condense everything down into this range. So mp.fft.fft frequency in dot shape -1. This is what is the length of n. So how long is our signal? Condense that down to an actual set of frequencies, and now we're ready to plot it. Plot frequencies. SP is the result of the Fourier transform is a complex number. If we want to visualize it, the best thing to do is just get the real component of it. plt.plot and plt.show. No, let's go ahead and run it. Yeah. And there we go, man. We got a nice clean Fourier transform of our signal. Turn around here and see. So why are there two of them? Yeah, right. Because the Fourier transform is symmetric, so we get that on both sides. Okay, cool. So there we go. So we got our Fourier transform. We're able to visualize it. That's pretty much it, man. Okay, I'm going to post the assignment this evening. I just need to type it up. But basically, what I want you guys to do for your Python project this week is I want you to write me a song, man. So everyone understands that music is subjective. Yeah, I will. Yes, absolutely. We will play my favorites in class. Yes, Edward, that's correct. Yeah, Andres, I'll try to, let me run it again and I will try to share that window with you. Yeah, I'm just gonna do this. I'm gonna hop over and change windows to the figure. Look at the figure. Yeah. Okay. So there's the figure for you guys in the Discord. Just got two spikes, like we said, because Fourier or the FFT is symmetric, you're gonna get a negative peak and a positive peak. So the fact that we see two peaks symmetric across the zero means that we just got one single sinusoid. So we can do all kinds of weird stuff with that after the fact. Yeah, okay, so back to the project. I'm going to type it up this evening. But yeah, you're going to play a song. What I want you to do is, music is subjective, but also musical notes, you can look up a table of musical notes, right? C is 440, and then it kind of goes on from there. You can see what the frequencies are of the different notes. Find a piece of music, and then just like we did in this, if I go back to our code, right? We defined up here, lines 31 to 33. We don't have to change the sample rate necessarily, but frequently we did 3 seconds of a note C, right? There's some musical, but you can you guys know what to do. But that's what I want you to do. I want you to do at least 3 seconds of some song. You're going to build it by building the signals and then sort of stacking them, end on end. You can be as creative with that as you want to be. You can be as sophisticated as that as you want to be. I like, Mary Had a Little Lamb will get just as good a grade as, Beethoven's Fifth Symphony. Now, you know what? I'm going to add an extra credit. I'm going to add a bonus. If you can create 2 voices. Yeah. So do you guys understand what I mean by voices? Not really. So a sine wave and a square wave. So timbre, so frequency is the frequency, right? Timbre, the sound that it makes is based on the, in fact, I don't even want to make it extra. I'm going to make it, I'm going to make it extra. Timbre, the sound, like a violin sounds different from a trumpet, right? Because the shape, even though they might be both playing, they might both be professional musicians playing perfect C at 440 hertz, you're going to notice a difference. A violin sounds different than a trumpet. And the reason that is that the waveform, despite the fact that they're both 440 hertz, are different shapes. Right? A violin produces a different shaped waveform as a trumpet does. So what I'm challenging you to do is create a song that has 2 different, a duet, if you will. Have a sine wave, and then you can use something you can be creative, or you can be kind of simple. A square wave or a sawtooth wave will create a different sound than a sine wave will. And if you play them together, you'll get 2 voices playing in harmony. So, but I'll make that extra credit. If you want to just do a sine wave that's playing Mary Had a Little Lamb, that's an important thing. The important thing is that you can use Python to create an array that is a discrete time signal that does something interesting and plays it out. And then I want you, that signal that we use to write, I want you to play it in your script just for fun. But also I want you to have it become a .wave file. So there's a write function that goes along with this wave file.read. There's also a wave file.write. Use that to take it and make it into a wave file that I can just play for the class. And then we'll play our favorite songs on next Monday. Cool. Oh, that's actually all I've got for you guys today. Don't forget, so I'll post an assignment this evening after I finish writing it up. No class on Monday because of the job fair. I'll see you guys on Wednesday. We'll start in chapter 3 where we're going to talk about the Z transform. And then this project will be due next Friday. So, anything from you guys? Cool. All right. In that case, that is it, man. I'll see you guys on Wednesday. Enjoy your weekend and have good luck.